Chris McClellan talked a little bit about this yesterday, but there's something nice about just saying reflectance as opposed to saying spectral bidirectional reflectance factor, or spectral bihemispheric reflectance factor, or spectral biconical. It's just easier to say reflectance. So we're going to talk today about the concepts and background of reflectance. This is what not sure why that mouse was moving around there. So reflectance is a very straightforward process. In this room, what object has what you would think is the highest reflectance? Whiteboard behind it, the screen. Good. So you basically understand the concept of reflectance. It also happens that there's some color effects in there, and so like this table is a high reflectance in part of the spectrum relative to other parts of the spectrum because it's brown. But basically all we're talking about is ratio, and as long as you have the appropriate units in both the top and the bottom, you will get a reflectance, and it's the amount of energy coming off of a surface divided by the amount of energy that came in. And you just have to make sure that you're keeping track of your units and you're keeping track of all of the terminology that you're using to do this. Now, having said this, and if you're reading this or listening to what I'm saying, there's a geometry effect that is built into all of this that is very subtle and very important in some cases. Now, fortunately, when we do reflectance-based calibration, a lot of this we can allow ourselves to just say reflectance because it simplifies because of the places that we are going and the test sites that we are using. What's also important is that we're using a radiative transfer curve, and that was that black box. And Martin Bachman, who joined us today, why don't you raise your hand, Martin, and so you'll get to see him after the break. We tried to make sure that every day somebody else spoke for a little bit to hopefully slow me. And that was the problem, was we let Chris go too early in the day. I think that was the mistake. That allowed me to keep speeding up during the day. Every time I start over, I slow down, and then I speed up. And so having Martin go after the break will give us a reset. And he'll go through the radiative transfer. And the radiative transfer needs a very specific kind of reflectance. And that's really what you have to decide. And in terms of what I know is it's a true bidirectional reflectance that has to go into the radiative transfer code. And you'll get that terminology in a little bit. But we have cases where there's a hemisphere coming onto the surface and a hemisphere going out. And that's albedo. And technically albedo is also integrated across all wavelengths, depending if you talk to a weatherman or a meteorologist. You can have spectral albedo, which is, again, but it's still, you have a hemisphere in and a hemisphere out. It's a bihemispheric situation. The other extreme is bidirectional. You have only a single direction coming in and a single direction going out. That case is impossible, but we can get close. And then it's a matter of how do you figure out what's incident and what's reflected. And in our case, we're going to try to make measurements. And that's then going to define what geometries we have to work with. And then the real problem is measuring, when you think about it, so we're going to measure the amount of energy coming in. Let's go bi-direction. So we'll measure one direction coming in and one direction coming out. How could you do that? Just think about it. If I gave you an instrument, one instrument, that's a radiometer, what would you likely do in order to try and measure bidirectional reflectance? You take the radiometer and you point it in the direction you're interested in of the incident light, and then you point it at the direction that you're interested in coming off of the surface. But maybe there's a gravitational effect that causes the instrument to look differently. Maybe there's a time difference in terms of the incident energy. Maybe there's a thermal effect in the radiometer. Maybe I don't actually have the right geometry looking up, and it's different from when I look down. And that's what makes all of this difficult in terms of trying to measure reflectance using instrumentation. Somebody goes, well, what if we took two radiometers? Then we could do simultaneous measurements. But how do I know the two radiometers are working the same way together? Now I have a cross-calibration problem. So what I'm going to talk about is reflectance factor. The reflectance factor is a cheating way to avoid the problem of the radiometer looking in two different directions or trying to do it in absolute measurements. Right? And the range of transfer code, what we're going to try to do is get to this what we call bidirectional reflectance distribution function, VRDF. Real quickly, so I know I'm going fast on this one, but I'm going to basically say is we have specular surfaces, like a mirror. We have Lambertian surfaces, and we're going to talk a lot about Lambertian surfaces. And it's called Lambertian because the guy's name is Lambert that figured it out. And so there's nothing special about that. And then there's real life on the bottom. Near specular, water. Waves and ripples, and you get a little bit of light going off in some other directions besides the specular direction. And near Lambertian. So I'm going to assume that I have Lambertian surfaces, but everything I have is really near Lambertian at these test sites. And then the geometry. I just put all of them up here, but really what we're going to do is concentrate on the biconical case, and also the conical hemispheric, or likewise the hemispheric conical. So it's in terms of how the light is coming in to the surface and how the light is leaving the surface. The first one is in, the second one is out. So a hemispherical conical is a hemisphere of light in and a cone coming out. And then biconical, conical in, conical out. Lambertian surface, there's a little bit of a font issue there, but this is the definition in terms of the intensity coming off of the surface. I'm not a fan of the intensity definition because very few people use intensity. I like radiance. And the key in terms of the beauty of when you do it in radiance is that no matter what angle you look at a Lambertian surface, the radiance is identical. So once again, if you had to maybe decide what material in this room is really close to Lambertian, which one do you think it might be? I can stand over here and I can see my charts. Everyone in the middle of the room in the back can see the charts really well, about the same. It's pretty amazing that they were able to develop something no matter where I go. And there's a little bit of a specular. When I stand here, I can see a little bit of a bright spot, a backscatter, but it stays pretty uniform no matter where I go. This table, on the other hand, I would not call it near Lambertian, because most of you can probably see a reflection of fluorescent lights. See why I like teaching this part of the class? Because when you're sitting in a room, there's a lot more examples that we can go from. I can't, especially look out the window. Well, the drapes are drawn, so the atmosphere, there's a little bit of limitation on what we can cover, but in terms of reflectance, we can talk more about things that you can see. So hemispheric reflectance, I'm just going to put this up here, it's in the charts, and it just points out that in order to do a true calculation, especially in hemispheric spaces, we have to know what the radiance is in all directions coming off of the surface, and we have to know what the radiance is coming in from all directions onto the surface, and then integrate all of that. And if there's things we can do in terms of approximations, we can simplify that integration. But and if we go to a Lambertian case, so a Lambertian surface, then we end up with a nice simplistic formulation where the reflectance is equal to pi times the radiance of the reflected energy over the incident irradiance. And this factor of pi comes in from this cosine factor integration up on the top there. Right? Reflectance factor. So what's a really odd thing is, and this was developed purely by the metrologists as a way to basically get rid of the incident term in one regard. And the reflectance factor down here is, if we know what the reflectance factor of a given standard is, and we know what the radiant flux, the energy coming off of a sample is, and we know what the radiant energy coming off of the standard surface is, that will give us the reflectance factor. Where that comes from is we basically say, what would be the energy, if I have this incident energies coming in, what would be the reflected energy from a Lambertian surface? And how does my actual measurement compare to that Lambertian surface? That's what reflectance factor is. It is a really bizarre concept when you stop and try and understand it. but it simplifies a lot when we make some approximations about the material we're dealing with. If we have a Lambertian surface, then it would be, if I have a non-ideal Lambertian, might be a reflectance of 0.5, the reflectance factor would be the reflectance, because I have two Lambertian cases and they're going to cancel out. We'll talk some more about this as we go on, but it starts off with, the whole reason we do this is because it allows me to go into the laboratory and create a material that someone else has created somewhere else. In my case, the National Institute of Standards and Technology in the United States. They created a pressed halon sample. They measured its reflectance factor. I can reproduce that in my laboratory. So now I have a sample that I know the reflectance factor of. And I can basically bounce energy off of that material. And then I can put up another sample and bounce what I hope is the same energy off that material. And I can compute the reflectance factor of my sample. And that allows me to characterize the sample relative to a known standard. So just again, reiterate some of these. It's the reflected energy off of some surface over the reflected energy that you would have gotten if that surface were a Lambertian surface. It's a geometry thing. What's interesting is then you get a factor of pi L on the bottom here because that's a Lambertian reflected energy. And on the top, we would still technically have to do our integration over all of the reflected directions that we have energy from. Right? And I'm not going through every single text and every single view graph as much as I'm trying to point out some of the highlights, and then there's supporting material on some of the charts as well. So, reflectance factor, the hemispherical conical case. And what's really odd is this will give you the same answers we're going to see as the conical situation. Because all of the geometry is in the reflected energy. And what you do in terms of how the incident geometry comes in, the whole hemisphere part of this, comes into what the L's are, the radiances coming off of that surface. So if I have a conical amount of energy coming into a surface and I have versus a hemisphere, my reflected radiance will be larger in the hemispheric situation than it will be in the conical situation. But when I look at my equations here, I will never see a difference in the format of the equation itself. Because the format of my equation is only in terms of what's coming off of the surface. So here's the hemispherical conical case. Here's the conical hemispheric case, which if you go back a few, I'm not going to do that for you. So here's the hemispheric reflectance. And here's the hemispherical conical. Conical hemispheric. And you basically end up again with a pi L in terms of the bottom. That's our Lambertian surface. And we're integrating over the same integration as we had if we had a bihemispheric reflectance factor. And the only difference again would be the L reflected would be different here than it would be for the bihemispheric case. So BRF. If somebody says we're going to measure reflectance, and they have a panel somewhere in their hand or somewhere in their vehicle or somewhere, someplace, when they say they're measuring reflectance, they are in reality measuring bidirectional reflectance factor on the surface. Some of them might be doing hemispheric reflectance factor, but they're all going to be measuring reflectance factor, not reflectance factor. You may see it as BDRF. Thank goodness many people have stopped using that term, because the one that's really important is BRDF. And BRDF is bidirectional reflectance distribution function. BDRF is bidirectional reflectance factor. And so if somebody had been consistent, BRDF should have been BDRDF. And this one is BDRF. So I'm going to use BRF, bidirectional reflectance factor, but I'm going to be lazy and I'm going to just say reflectance. So from here on out, I will try to remember to say reflectance factor, but almost certainly everywhere you'll see reflectance. And I know I'm doing it, and I know I'm doing it wrong. It's just bad habit. Right? And geometry here is just the fact that it's a conical case, or the directional case coming out in terms of we can define how large of a directionality we have there. And so in this case, it's really a biconical, not a bidirectional, because there's a finite size to what we're doing. Reciprocity. This will play an important role in a couple of the charts I show later on. All that means is, if I make a measurement of the geometry, and let's say I do a hemisphere coming in and a directional coming out, and I get an answer. So that would give me a hemispheric directional reflectance factor. And I might decide that, well, it's actually easier for me to measure a hemisphere of light coming off of the surface and a direction coming in. And I can make that measurement and derive the other geometry. I can just reverse them. I can make the reciprocal. It's not a straight one-for-one. There's some calculations you have to do, but we can assume that we have reciprocity. Now, the people who make their living on reflectance, they hate reciprocity because, yes, the photons aren't following exactly the same paths and there's little nuance. In our world of 0.1%, this is plenty good. So reciprocity is our friend. It's going to allow you to make some characterizations that are easier to do than it is if we tried to do a more difficult measurement. This is, in Christianity, we have something called the Holy Grail, the ultimate thing we're trying to achieve. This is, if somebody gives you the true BRDF of a surface, you are done. You really never, and if you know as a function of time, you never have to go visit that site ever again. And BRDF is the bidirectional reflectance distribution function. It's in terms of the incident energy coming in, the irradiance, and it's the reflected energy coming off of that surface. And it's a directional thing. So basically you now have, this is what we need in the rates of transfer codes. Because the rates of transfer codes compute the energy coming onto the surface as the irradiance, and then it computes what goes off in all of the other directions using this BRDF. If we are a perfect Lambertian, so perfect means that everything is reflected. There's no absorption whatsoever. The BRDF is 1 over pi, and here's, it's per steradian. And don't let the per steradian confuse you too badly. It's related to the solid angle of the system. It's really a conversion factor because the radiance and the irradiance have different units. And this is the unit that's left over. And it's the directionality part of it. The really bad thing is technically steradian is a unitless unit. So it's even more confusing. If you actually do a computation of steradian, you'll never see it show up. You have to just carry it with you all the time. The bidirectional reflectance factor is pi times the BRDF. So now you see the beauty of, and it's not just for Lambertian. That's true all the time. And it has taken me decades, and it's still, even when I say it now, tonight I will spend an hour going through the derivation again just to prove it to myself once again. But it works. You can prove that this is true in general. So now you see why we like BRF. Because if I have the BRF, all I have to do is divide that by pi, and I have the BRDF, which is what I want for my rate of transfer equation. So metrologists sort of knew what they were doing when they put up this idea here. And so now if we have an equation in terms of the reflected energy for the Lambertian surface. So, and when I used to teach classes, this was, I called this the magic equation, I called this the most important equation. I basically allowed the students on the exam that if there was a question that they could not answer, all they had to do was write this equation anywhere, on any question, and they would get 5 points out of 100. No questions asked. That this is so important in remote sensing that it was an instant. It always bothered me when somebody got a 3-point question. I wouldn't give them more than the points of the question. They would waste it on a 3-point question. I never understood that. But they would get 5 points for just writing L equals rho E over pi. And then in terms of BRDF, L is equal to BRDF times the incident irradiance. So again, it just shows that you can see everything in here is self-consistent. But if you know this, if you know for all geometries, that surface is perfectly understood. So Lambertian makes everything simple. L equals rho E over pi. If I know the incident irradiance, I know the reflectance, divided by pi, I have the radiance coming off of that surface, and I can start doing my calculations. Is that the voice that's supposed to happen? Fireworks. Is it fireworks?
Somebody shooting fireworks off one of the apartments over there.
Oh, more interesting. We should watch that instead.
Yeah, it's Saturday, the 16th, yeah, probably the wedding.
So 16 is a good day.
Yeah, because even number is better. Good luck.
I'm glad my wife does not know that tradition.
Can I go back one slide? Two slides. One slide. BRN, I have BRCN. And you're saying that's true for all surfaces?
For all, in general.
Yeah.
So I mean in all surfaces, yes.
So if you know the BRN, you can calculate the BRDN.
Correct.
You know the BRN for one angle, for two angles. Right direction,
I know the BRF at 2 angles.
because you've got, you know these are two angle things. Zero
Correct.
point five.
Correct.
You're saying you can equate that to BRDN.
Oh, so what I should have put here is BRF of theta incident, phi incident, theta reflected, phi reflected is equal to pi times the BRDF of theta incident,
Okay,
phi
right.
incident. In other words,
Yes.
these two have to be, it'll be that same geometry. So the
Okay.
BRF for a specific geometry is equal to BRDF at that same geometry. So in the Lambertian case, we know what that would equate to. In the non-Lambertian, I can have a function for BRDF or BRF as a function of the angles, and that would just be a factor of pi between them. So it would be the same functionality, it just would be a factor of 3.1415.